So, as promised, here is part 2 of your wave PowerPoint podcast, Wave Behavior and Interference. Now we know all the parts of the waves, how to describe them, measure them, and analyze them, but how do they interact? Because waves, like other things, interact with each other and the environment around them. So we know the waves travel through mediums, but what happens when that medium runs out? Any guesses? There's something called boundary behavior. This is the behavior of a wave when it reaches the end of its medium. When one medium ends, another begins. That is called the boundary. One type of boundary that a wave may encounter is that it may be attached to a fixed end. That means the one end doesn't move. The only part that's moving is your part with a hand. So this part you can go up and down or left and right, depending on if you want to create a longitudinal or transverse wave. But this side over here is fixed, so it's going to stay where it's at. In this case, the end of the medium will not be able to move, which I just said. The end of the medium. The medium is the string. Here's the end. So what is going to happen if a wave pulse goes down the string and encounters the fixed end? Think about it. Picture it in your mind. What's going to happen? So here, the incident pulse is an upward pulse. The incident pulse is the one that you give it. So it's the very first pulse. So I just jerk it up one time. It's going to create this nice little hump here. And it's going to travel all the way down the medium. And when it hits the fixed end, it's going to reflect. And this reflected pulse is going to be upside down. And I can show you this with a string, or I can show you with a slinky in class. So why don't I do that? So the reflected pulse has the same speed, wavelength, and amplitude as the incident pulse. So however much energy you give it in the incident pulse, the reflected pulse is going to be the same. It's going to come back at you with that same amount of energy. So this wavelength from here to here, it's going to be the same as from here to here. The amplitude from here to here is the same as from here to here. And it's going to have the same speed coming down as it does coming back. Now that's in a perfect world. And in physics, we neglect things like friction because, it's a pain in the butt to deal with. Here's a little animation of it. The pulse travels down the medium, hits the fixed end, inverts itself, and comes back the other way. Very exciting, high definition graphics. Another type of boundary is when a wave's medium is attached to a stationary object as a free end. In this situation, the end of the medium is allowed to slide up and down. So this time, instead of being tied here stationary, this part can go up and down. So what do you think is going to happen in this case? Picture in your mind, think. You're all bright, intelligent people. You should be able to figure this out. So in this case, the reflected pulse is not inverted. It is identical to the incident pulse, except that it's moving in the opposite direction. So everything's the same. So the speed, wavelength, and amplitude are the same. The wavelength, the speed going down is the same as the speed coming back, and the amplitudes are also the same. And this is what this guy looks like. It's better than most television programs to sit here and watch this. You can also change the medium as a boundary condition. In this case, we're moving from a less dense material to a more dense material. So think of a thin rope attached to a thick rope. The point where the two ropes are attached is the boundary point. At this point, a wave pulse will transfer from one medium to another. Duh. And what do you think is going to happen here? This one's a little trickier to figure out. So what do you think is going to happen? Say it out loud. I know you're all sitting in your homes or in study hall right now, saying this out loud. So whenever we change the medium, part of the wave is reflected and part of the wave is transmitted. So here comes the wave down. It's going to hit the boundary. But part of it is going to keep going through that boundary. A lot less of the energy. You can see the amplitude's a little smaller here. And some of it's going to be reflected too. This amplitude is smaller than this guy too. So part of the wave energy is transferred to the more dense medium, and the rest of that energy is reflected back. So the transmitted pulse is upright, while the reflected pulse is inverted. So when you're doing this guy, your incident pulse is going to hit this medium, and it's going to act like the fixed end boundary condition for the reflected part. It's going to push it back, but it's going to be inverted. And it's still going to keep going through this more dense material, but with much less energy. That's why the wavelength and amplitude are smaller. So the speed and wavelength of the reflective wave remain the same, but the amplitude decreases. So this wavelength from this point to this point is the same as from this point to this point, but the amplitude's smaller. But it's still going to still go down with one speed and come back with that same speed. On the other hand, though, the speed, wavelength, and amplitude of the transmitted pulse are smaller than the incident pulse. Everything's smaller. It moves slower, it doesn't go as high, and the wavelength's a lot smaller too. So the only thing that changes on the reflected pulse is the amplitude, and everything changes on the transmitted pulse. And again, high definition for you. There's the incident pulse, hits the medium, part of it comes back, some of it keeps going. Exciting. Now, waves also interact. All we have left to discover is how this happens. When two waves meet while traveling along the same medium, it is called interference. Much like an interference call in football. Something interacting. You have pass interference. Whenever the defender interacts with the receiver, and you get a timeout, or sorry, penalty. And they're usually BS calls. And there's different types of interference. First, we're going to talk about considering waves that move towards each other, both having a positive upward amplitude. So what will happen when these two guys meet? Think about it. You got one wave coming one way, another wave coming from the opposite way. Both of them have the upward humpy thing. So they will add together to produce a greater amplitude. The amplitude of the whole wave when the two meet is going to be greater than the amplitude of either one of those. Here's a little picture of what that might look like. The red wave is going to the right, the blue wave is going to the left. They're going to meet in there. And when they do meet, you add their two amplitudes together and you get this green wave. So this is the resultant wave, the green one, whenever you add these two amplitudes together. You'd also have downward humpies, if they're both downward, one going to the left, one going to the right. The overall wave is going to be this bigger green downward humpy. And this is known as constructive interference. They add together, it's constructive. But we also have destructive interference. And this is when we consider the opposite. There we have two waves moving towards each other, one having a positive upward and one having a negative downward amplitude. And I'm pretty sure you can figure out what's going to happen when these two guys collide. So this time when they add together, they'll produce a smaller amplitude. And as I said, this is known as destructive since they're going opposite ways, they don't like each other. They cancel each other out in some points. Now here, we have two waves, one going left, one going right. They both have the same amplitude, but one's up and one's down. So whenever they meet, they totally cancel each other out. So it's just a nice flat line in there. There's still energy going both ways on this, but for that point in time, they both cancel each other out, so it's nice and flat. A little bigger so you can see it. Now this time, we have a smaller amplitude for the one going to the right, and a bigger amplitude for the one going to the left. Now this time, whenever they hit, they're going to produce a net downward amplitude for the destructive interference. So this green represents whenever you add the red and the blue together, this is what's left over, because this amplitude for the blue one is much bigger. So for the first one, before the interference looks like this, and after the interference, it comes back looking to the same way. We saw the blue wave going to the left, the red wave going to the right, and they're back to their original amplitudes. So checking your understanding. What happened there? So which one of these points represent where constructive interference is going to happen? Think about it for a second. So constructive interference, they're going to add together, produce a greater amplitude. So this is going to happen at points G, J, M, and N. So at point G, both amplitudes are upward. At point J, both amplitudes are negative. M, both are negative. And both are positive. As long as they both have the same sign, they're both on the same side of the equilibrium line, which is this guy again, the horizontal line. It's going to be constructive interference. Now for destructive interference, which points do you think they're going to be? Pretty easy to figure out. H is the first one. This one has a negative amplitude. This one has a positive amplitude. They have different signs, so it's destructive. I, same thing. This one has negative, positive. They're going to destruct each other. And K, L, and O are the same way. Negative, positive, negative, positive, negative, positive. And that's the end. So now we're going to do a problem involving the superposition of waves. Superposition is what it's called whenever you add the two waves together. So here's three cases drawn here. These are nice little square waves, so these guys are going to be easy. I'll make you do harder ones in class. And we want to draw the superposition of the waves whenever the two waves exactly overlap. So each of these waves has the exact same width. So we want to draw them when their centers are over this dashed line. We're going to do this by first drawing both waves as they would appear at the center and then adding them up to see where the resultant wave will be. We're going to do this by drawing a series of dots to where the new wave should be. It may seem a little unnecessary to do it for this problem because these guys are pretty obvious what the waves are going to look like. But the ones I'm going to have you do in class are going to have like ramped waves, a ramp and a square, maybe some curves. We'll see. So you want to draw the dots and then you want to connect the dots. Which is why I have this lovely cartoon show from my childhood, Pee-wee's Playhouse.
Hey, Magic Screen, you want to play? Sure, hop in. Connect the dots, la 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 la. Connect the dots, la la la. Hey, it's all done. Looks like some type of sled. Hey, it's a dog sled. That's at the North Pole. Mush!
Yes, Pee-wee's Playhouse was a very strange show, Saturday morning cartoon for my youth. But anyway, we're going to draw these superposition of these two waves and try to, get over the horror of what we just saw. So first thing we want to do is we want to draw each wave as they would appear when they get right to the center here. And these guys are pretty easy. So we'll draw a nice little line here. The first wave, this guy we'll be working with first. We'll do him in blue. And let me change it to this guy. So he's 4 across, so obviously he's going to have 2 on each side, and he's too high. So when he's at the center, it's going to look like this. And why is it not drawing in blue? I do not know. So there's the first wave. The second wave is going to be exactly over top of it. So we really don't have to draw anything for this guy. I wish I could change the colors. Let's see if this works. Blue. There we go. Blue. And blue. We'll do the second guy in red. So whenever we do that guy in red, it turns this purple. Because red plus blue equals purple. So now we got a purple wave. Now, since 2 plus 2 equals 4, our superposition wave will be 4 high at each point. Draw this guy a little bigger. We'll do the superposition wave in green. So it's still too big. There we go. Connect the dots. One there, one there, one there, one there, and one there. So our superposition wave, we will do completely in green. Will look like this. So there we have it. A nice green superpositioned wave. That looks something like that. So this one was easy. The next one's easy too. Again, we'll draw the left wave in blue. Now that I finally figured this out. The left wave, when it gets over to the middle again, it's going to look just like the last time. The next wave is going to be the same thing, but on the other side. We'll do him in red. Two minus 2. The resultant is 0. So we have 0 for here, 0 for here, 0 for here, 0 for here, and forgot this guy right here. So our resultant wave, these two totally cancel each other out, and we're left with nothing. So we have a nice green wave like that. Now the last one is pretty easy too. Again, we'll draw the left one in blue. It's the same as it has been. We'll do the right one in red. This one goes down 4. 1, 2, 3, 4, 4, and 4. So now we want to draw some dots. 2 and minus 4 gives us minus 2. So we have minus 2 the whole way across. And our superpositioned wave is going to look like this. Keep drawing red. It's not going to work. Connect the dots, tra-la-la-la. Alright, and there you have it.